In fact, one of the interesting things about ionic species, when they become ionized, remember, we always look to see what is the nearest noble gas, and then have them have that same number of electrons. So if you consider nitrogen, oxygen, and fluorine, where they are in the periodic table, let's jump over there. Nitrogen, oxygen, and fluorine. Remember the little trick I showed you to how to predict what ion will form is that it's trying to get to its nearest noble gas, which in this case is neon. So in order for nitrogen to have the same number of electrons as the nearest noble gas, it needs to gain 1, 2, 3 electrons. So it'd be N3 minus. Oxygen, to become oxide ion, would need to gain 2 electrons, 1, 2. Fluorine would need to gain 1. If you look at their electron configurations, this is the abbreviated electron configuration for nitrogen, oxygen, and fluorine. 2s2, 2p3, 2s2, 2p4, 2s2, 2p5. When they become ionized, they're gaining 3 electrons, 2 electrons, and 1 electron. Well, where are those electrons going? They're going into those outermost unfilled shells. Well, the innermost unfilled shell, I should say. So the innermost unfilled shell. And so all 3 electrons for nitrogen will go into this 2p. All 2 electrons for oxygen will go into this 2p, and then the single electron for fluorine will go into this 2p. When that happens, their electron configurations will be as follows. They look the same, don't they? They're all helium, 2s2, 2p6. They're all the same. And so these are what are called isoelectronic species. Again, consider this for magnesium, sodium, magnesium, and aluminum. Again, sodium, magnesium, and aluminum all in the same row. They have these particular electron configurations: neon 3s1, neon 3s2, neon 3s2, 3p1. Sodium is going to want to lose 1 electron. Magnesium is going to want to lose 2 electrons, and aluminum is going to want to lose 3 electrons, right? Because they're all trying to have the same number of electrons as neon, the nearest noble gas. And so 1, 2, 3, 1, 2, 3, 2, 1, and 2, and sodium 1. All right. So when they lose the electrons, the place they lose them from is from the outermost shell. And so comes sodium plus, magnesium 2 plus, aluminum 3 plus. Look what happens. 3s0, 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 3p0, or in other words, these now become empty subshells. So empty subshells. They all essentially have the noble gas core of neon. And so all of these ions right here have the same electronic configuration. They all have the same electron configuration as neon. And so these are all what are called isoelectronic species. Now if we think about the smallest, the largest one in this case, they all have the same number of electrons, right? And they're all in the same electron configuration. So which one's the smallest, which one's the largest? Well, it's in this order. The reason why is if we look at these, we consider what's pulling in those electrons again. It's the protons at the nucleus. Well, which one has the most protons? Well, if we look at the periodic table, we'll see aluminum has the most protons. Aluminum has 13 protons. Magnesium has 12 protons. Sodium has 11 protons as we move down. So the smallest is the one with the most protons. It's pulling in the same number of electrons, aluminum 3 plus pulling in the same number of electrons as nitrogen 3 minus, but it has more protons or more pull to do it with. And so this is the type of trend you'll see for isoelectronic species and their ionic radii.